abstract book, it said the importance of orthopyroxene. Now he will tell us why plate tectonics occurs on Earth.
Okay. Thank you very much. Good morning. Thank you for inviting me to this nice meeting in a very nice place. Actually, this morning it was really good. I took a little walk around the hotel. It's beautiful. But also I realized that things fall. Heavy rain this morning, is that right? Okay, so let's change the gear a little bit. So we are going to discuss my talk and the following several talks, a little bit about the microscopic aspects of geodynamics. And in my talk, I'm going to discuss some of our new results, which address the question of why plate tectonics occur on Earth. This is related to what Paul Tuckley discussed yesterday. That is we all learn plate tectonics operates on Earth, and then we typically assume that's obvious, but this is not really obvious, as Paul discussed a little bit. I'm going to elaborate. The main point is the plate tectonics is a really very special mode of the mantle convection. And the most natural mode, in a way, of mantle convection is stagnant lead. And so in my talk, I'm going to discuss results from our experimental work to address this question, that is why the lithosphere of the Earth has so modest strength. And then particularly with emphasis on something a little bit beyond the conventional model. Conventional model, lithospheres are assumed to be homogeneous deformation in a deep part and localized deformation, pure origin. That model, as I'm going to show you, doesn't predict plate tectonics. So let's see. So the first is I'm going to briefly review plate tectonics and lithosphere strengths in general context, in a way geodynamic context. And then I'm going to emphasize that the standard model lithosphere strength, one of the best cited papers in this category is like the Kolstad et al. 1995. That model doesn't predict plate tectonics for oceanic upper mantle. And I don't want to discuss the continental part, but continental part, that model doesn't support the continent has survived so long time. So the standard model doesn't explain major features of the Earth, like plate tectonics and the long time survival of continents. But in this talk, I'm going to focus on the oceanic part, and then I'm going to discuss which aspects of the model might be incorrect. And then I'm going to briefly discuss new experimental observations in our laboratory, and then show you some results by which we have a laboratory results to indicate that under some conditions, actual strength of the lithosphere can be significantly lower than standard model predicts. And a key player in this business is OPX. For geodynamicists who may not know what OPX means, OPX is orthopyroxene. Okay, I guess you guys know already. OPX is orthopyroxene, secondary mineral. Okay, and then after showing the experimental results, I'm going to discuss briefly basic physics behind weakening, because always question is in our laboratory we can do really nice, interesting experiments showing weakening, for instance, but those are very fast time scales and different conditions. So therefore, we need to understand basic physics by which we can do some extrapolation. So there will be some discussion on the scaling business. That is, in a way, theory for weakening. The starting point is the plate tectonics is the one type of the mode of mantle convection. And of course, plate tectonics is very important for us because unique part of plate tectonics is the this is one style of convection where surface layer is also involved in the convection. So the surface lithosphere does subduct into the mantle, and then large-scale circulation of matter occurs. And then, for instance, the volatile could circulate very well if plate tectonics mode occurs. So some people believe that plate tectonics is one of the key issues, key factors by which the origin of life is controlled, because volatile circulation probably stabilize the surface ocean and then control the condition of the atmosphere. However, really important concept is that plate tectonics is not obvious mode of mantle convection. As I'm going to show you, as Paul Tuckley also discussed, there are various styles of the mantle convection, and plate tectonics is only one of them. And if our surface layer, namely plates, are so strong as you might expect from low temperatures, then simply surface layer is so strong, surface is just dead, rigid. And this is called stagnant lid. And surface temperature is low, as we know. So therefore, the stagnant lid mode of convection is, in a way, more natural mode. Okay. So this is the schematic diagram based on some numerical modeling of the mantle convection, in which this is Slava Sonato from the Luis Moresi classified mode of mantle convection based on two parameters. The key concept here is if you are dealing with the constant viscosity fluid, and if viscosity is very large, you can characterize convection mode of convection by only one parameter, Rayleigh number. But as you know, the viscosity of Earth's materials are very sensitive to the temperature. So characterizing convection by one parameter, Rayleigh number, is misleading in a way, because Rayleigh number has a viscosity in it, and viscosity could change tens of orders of magnitude. So using one number is misleading, at least not sufficient. So in this paper, they try to characterize the mode of convection by using two parameters. One is the Rayleigh number corresponding to hot interior, and then another one is the viscosity contrast, which captures the temperature dependence. So if this is large, which means the surface is much stronger than interior. So temperature dependence is characterized in this model by one parameter. Then they could classify mode of convection into three categories, and somewhere narrow regime plate tectonics like style of convection occurs. So one message is, without going into detail, one message is plate tectonic style of convection occurs only limited parameter space. If the temperature dependence is so strong, in this regime, you go to the yellow regime, which is stagnant lid, because surface is so strong. So stagnant lid mode of convection is this way. Surface is so strong that the convection does occur inside, but not the surface is not involved in the convection. If, however, the surface layer is little strong, but not strong enough, then through the convection, surface may be broken into various plates, and if plates are, again, weak enough to subduct, then surface layer could be involved in the whole mantle convection. So this is the plate tectonics. So plate tectonics mode occurs only when surface layer is modestly strong. And of course, surface layer has a semi-viscosity as the interior. Every part just moves around, and there's no plate. Okay, so that's a very simple version. But anyhow, so the main points are, based on the understanding of material properties, we may expect stagnant lid mode as a very natural mode of convection, or a plate. But in order for plate tectonics mode to occur, lithosphere has to be relatively modestly strong. It can't be so strong. And in terms of numbers, this number appears to be dependent on some details, like continents. But as far as I understand it, if you use very simple scaling, analysis in which you evaluate the driving force of plate subduction and the resistance, and then you come up with the roughly about 100 or 200 MPa if you parameterize the strength of the lithosphere in terms of the yield stress. If lithosphere is less, strength of lithosphere is less than roughly 200 MPa, then plate tectonics mode of convection occurs. If lithosphere is something like 500 or 1 GPa, it's so strong for plate tectonics to occur. So the mode of convection is controlled by if convection occurs, there must be some balance of force or energy dissipation. Convection is driven by gravitational energy, and by convection you have to dissipate energy by plate deformation or interior of the plate. And then you have a choice of two modes of material flow. One is surface is just rigid and the interior is deforming, but you could also add the surface deformation. Then you can ask at which condition surface could be involved in the convection, which is the plate tectonic mode. And the answer is if the surface is modestly strong, not as strong as like 1,000 MPa. So this is the condition for plate tectonics in a very simple term. And then you can take a look at what we can get from the laboratory experiments. As I said earlier, this is a very famous paper by Del Costa. They constructed this model, classically, it's essentially based on Chris Getze, the MIT, his approach to show how to construct a strength map. Chris Getze developed this concept mid-70s. And they followed Chris Getze's idea, and what you can see is that in shallow part, strength is controlled by brittle fracture, and so therefore the strength increases almost linearly with pressure. And then the deeper part, deformation or strength of the material lithosphere is controlled by ductile flow, in which strength is dependent on temperature, so that as you go to deep, temperature goes high, therefore strength decreases. And also, there are a couple of assumptions. Also, they assumed when they constructed this map that lithosphere is made of pure olivine. Okay, and brittle part actually doesn't matter, the olivine or OPX. Brittle part, amazingly universal law for brittle part is that strength is almost independent of material. This is called Bayer's law. However, the deeper part, strength doesn't matter for which material you use. But anyhow, so when you use olivine, you get this profile. And actually, in this diagram, in a way, they cheated. They are following what the calculation tells them, what the profile they should be. This strength goes here, and this one goes up here. So you would get higher than 1 gigapascal. And if you read this paper, I don't think they explained this. They probably felt, oh, this is uncomfortable, so they chopped off by hand. So no theory at all for this. But even for this, average strength is several hundred MPa. It's too strong for plate tectonics to occur, because this is the maximum stress below which plate tectonics occurs. So conventional model is inconsistent with plate tectonics. This is a problem because plate tectonics is perhaps the most important phenomenon in terms of geodynamics, and we believe that plate tectonics or mantle convection is controlled by rheological properties. But if the standard model of the rheological properties is inconsistent with plate tectonics, this is a serious problem of geodynamics. So this is the issue which I'm going to discuss in this talk. So when you have some problems with the well-accepted model, then you have to go through what kind of assumptions they made. And the first is they made assumption that the lithosphere is made of olivine. And if you learn the petrology, you're going to learn that upper mantle is not only olivine, but other minerals like OPX, orthopyroxene. And as I'm going to show you, a few years ago, we showed that OPX is significantly weaker than olivine under lithosphere conditions. And OPX occupies something like 20-30% of lithosphere, which is close to so-called percolation threshold. Okay? So if you have a mixture of strong and weak material occupies close to percolation threshold, then there is the opportunity that weaker phase might control overall strength. And another assumption they made is the homogeneous deformation, okay, and no shear localization. However, geologists know that if geologists look at the deformation features on Earth, almost always deformation is localized along shear zones. So you need to address the issue of shear localization or weakening when you want to revise this kind of picture, which is inconsistent with the most important feature of the Earth. And another thing which is a little bit questionable is the assumption of dry rheology. This is a little tricky business because on the one hand, we have very strong indication that oceanic lithosphere is pretty dry because water is removed by partial melting at mid-ocean ridges. But in more detail, lithosphere is not completely dry, and there's a little bit of water. And I'm not going to discuss too much because I don't have much data on it. But a little bit of water might affect rheology. That's a potential problem which we are going to address in the future. Okay, so this is the problem of the existing model. So what we need to do is this conventional model predicts too strong lithosphere so that plate tectonics cannot be explained. So we like to find out which way we can explain plate tectonics. In other words, we like to find out what is the plausible way or ways to reduce the strength. And one option is we have two branches, brittle failure and then the ductile. So the one possibility is how about reducing the strength in the brittle branch, which is a fracture strength, okay, or frictional resistance. And another possibility is the reducing strength in the ductile regime, this branch. Brittle branch, many people argued that weakening in this regime is very important. I do not disagree with them. But the degree to which you can reduce the strength in the brittle regime is not that high. It's limited because this standard model assumes that pore space is filled with water, liquid. So the pore pressure is the hydrostatic pressure. So in a way, not strictly, but in a way, it's highest pore pressure effect. So the one common assumption to argue the weak strength is the resistance for sliding is controlled by friction coefficient and effective pressure acting on the sliding plane, like fault plane. And the effective pressure is the real pressure minus pore pressure. And if pore pressure is very high, then you can reduce this P minus P pore, by which you can reduce the resistance for friction. But in this model, the pore pressure is already, in a way, maximum. So you cannot reduce this strength so much. Plus, this factor, several people argued that reducing friction coefficient may be very easy, efficient way of reducing strength. But at least a new result from laboratory experiments show that this friction coefficient, even for hydrous minerals like serpentine, is not that low compared to the standard model. This is the experimental results by Chermak and Hirth to investigate the friction coefficient in serpentine. This is the confining pressure and differential stress, and the friction coefficient corresponds to this slope. And a conventional model for friction strength is so-called Bailey's law, where friction coefficient is assumed to be something like 0.6. And so they determine the friction coefficient for serpentine at low temperatures. It's not that different. And the friction coefficient becomes low only at very high temperatures. But the brittle branch is the low temperature, so that high temperature results are not applicable. So as far as this study is concerned, the reduction of friction coefficient by hydrous minerals, at least for serpentine, is not that efficient. Okay. So my conclusion is the reduction in ductile regime is not that efficient. So let's focus on plausible mechanisms of weakening in ductile regime. As I suggested earlier, based on our laboratory experiments, orthopyroxene, secondary mineral in the lithosphere, has much smaller strength than olivine under lithosphere conditions. And so therefore, you might speculate that OPX might help reduce the strength. That is one possibility. And also the well-known concept by which you can imagine weakened material is the grain size reduction, because ductile strengths of materials are sensitive to grain size, and if you have processes by which you can reduce the grain size significantly, then sometimes you can reduce the strength. And this effect could be very large, because in a grain size sensitive regime, viscosity, if you define viscosity, is proportional to grain size to the power of second or third. So it's a very large effect. And as I said earlier, in many shear zones in real Earth, we do see correlation with the shear localization and grain size reduction. Okay, so what we did was to understand a possibility of those two processes. One is the load of OPX and grain size reduction. We conducted laboratory experiments on the deformation of olivine plus OPX mixture to see how OPX may modify the manner of deformation. Okay, and so those are our results published last year to show OPX with certain orientation is much weaker than olivine. So this is the this is what we often do. We deform two materials together. This is olivine and OPX in two layers, and then we shear two layers in this way. And if the strength is different, by just looking at the strain marker, which was originally vertical, you can see which one is the weaker. So this is a really clear demonstration that OPX is much weaker than olivine. Vertical line means OPX was not deformed at all, and olivine was not deformed at all, and OPX was deformed from vertical to this one. Okay, so OPX is much weaker. And we conducted this type of experiments under certain temperature and strain rate stress range. Then we established the flow laws for olivine and OPX. And the conclusion is this strength contrast is getting larger as they go to lower temperatures. So this is a very favorable condition for lithosphere to help reduce the strength. And given that, then you can speculate various ways by which rocks might become weaker. For instance, in a pure olivine, you may create fine grains by deformation, so-called dynamic recrystallization. And if those fine grains are connected, you may end up with a weaker whole rock. But if you have a mixture of olivine and OPX is weaker, and if you have a connected OPX, you may end up with a very weak rock. And the third possibility is that this is what we found actually. If you have OPX and olivine mixture, you may end up with the fine grain formation in both olivine and OPX. And if these fine grains are mixed together, then you develop the fine grain regions where two phases are mixed. And mixing of two phases is a very efficient way to stabilize fine grain state so that you can enhance the degree of weakening. So those are three possibilities which we speculated before we did the experiments. And the importance of OPX is also recognized by the study of naturally deformed rocks in shear zones. And if you go to shear zones, typically, you can find very thin layer where deformation is localized. And quite common observation is if you focus on highly strained region, you tend to see the mixture of many minerals. And if you go outside of this, if you have a single phase region like olivine rich, deformation is not much large compared to this layer. So this is really common observations. This is another, from another paper, you can see this is the microstructure from the shear zone. You can see very well a mixture of olivine and OPX. Okay, so those are motivations. So therefore, we have conducted laboratory experiments in my lab. Starting like 1 or 2 years ago. And then we have very thin layer of sample, put it into high pressure and temperature conditions, and deform it very slowly to large strains to see what kind of strength evolution we may detect through deformation and what kind of microstructure evolution should be associated with it. So those are the results to show. So this is a plot of the strength versus strain. If you start deformation, material becomes large, strong, and then if it goes to steady state, it's going to be flattened out. So typically, a high temperature experiments, we got the saturated stress. However, as you can see in this diagram, if you deform the rock, low temperature, 1000 degrees C, just continuous hardening, nothing happens. Like a weakening happens. And 1100 degree, substantial weakening, and 1200 degree, again substantial weakening. And a little bit surprising, but I have an explanation for it, is that if you go to very high temperature, like 1300 or 770, no weakening at all. Okay? So the main conclusion from this experiment is the weakening occurs in a temperature window. Okay? If temperature is too low, of course, nothing happens because it's so strong. But also, if the temperature is too high, weakening doesn't occur. Okay, so those are the mechanical data. And then we took a look at the microstructure to understand what happened. So this is a starting material, a mixture of olivine and OPX. Very nice microstructure. If you do an experiment, you can see this is a really nice equilibrium microstructure. And then after deformation, this nice microstructure is distorted, and the grain boundaries are serrated, and the internal strain develops. And as you can see, OPX, this is the pink region, and yellow is the olivine. And even after gamma 1, strain 1, OPX is really highly deformed. So the strain is very heterogeneous. And fine-grained OPX grains were produced, and then those grains flow along the pre-existing grain boundaries. And those are microstructures, which corresponds to rheological weakening. In these cases, we have substantial weakening. And those microstructures, which indicates mixing of OPX and olivine, is very similar to what we observe in naturally deformed peridotype. Okay, and this is a diagram to explain what conditions weakening could occur. Essentially, weakening occurs in our interpretation when grain size of the material is reduced high enough, large enough reduced, so that grain size becomes large to small. And if grain size is small enough, you go into diffusion creep regime, where strength is grain size sensitive. Okay. And this transition occurs when the temperature is low enough, because at low temperatures, domain of the diffusion creep expands, because activation energy is lower than the diffusion creep regime. So if you go to high temperatures, this domain expands, and then even if the grain size reduction occurs, you never go into the diffusion creep regime. So this is a brief explanation of why we didn't see weakening at high temperatures. And however, in order to explain the weakening, we need to go a little more than that, because you may produce very fine grain size regime by which you can reduce the overall strength. But if the grain growth kinetics is so fast, this weakening occurs only just 1 second, and then you don't get any substantial weakening. So what you need to do is to quantify the influence of grain growth. I developed a very simple model to quantify this, and in this theory, regime or localized deformation and homogeneous deformation is divided by two lines, and the condition for localization are characterized by two parameters which have clear physical meaning. One is the parameter theta. I don't remember how to read this Greek, but theta, which is the diffusion versus dislocation competition parameter. Okay, and diffusion group has to dominate in order for grain size weakening to occur. The second parameter is the deformation and grain growth competition. If grain growth is so fast, you may end up with weakening, but the weakening finishes very quickly. Okay, so you have to have you have to characterize the weakening conditions by two parameters. So this is a very physically a clear picture of the shear localization. So if the Xi parameter is very large, the grain growth is so fast, you don't get the substantial weakening. Okay, and so this is a very nice way to understand the physics, but this is not useful because theta and Xi, you have no sense of intuition. So we can translate this diagram into temperature and stress space using some experimentally observed some parameters. Okay, and if you do that, this is the end result. So this is a translation of that diagram into temperature and the stress space. Okay, color doesn't show up very well. But the main point is that if you translate that diagram into temperature and stress state, for pure olivine, domains in which shear localization occurs turns out to be very narrow. The main reason is for pure olivine, grain growth is so fast. And however, if you add OPX, by which grain growth kinetics can be retarded, then conditions where shear localization occurs expands a lot. And if you like to compare this diagram with experimental results and natural samples, you can see that in experiments where the OPX and olivine mixed together, in our experiments, under high temperature conditions, we didn't see any localization. And of course, this is consistent with this theory. And under relatively low temperature conditions and high stress, yes, we did see localization. And we can also explain naturally occurring shear zone rocks by OPX and olivine, but the pure olivine model, you cannot explain natural rocks. Okay, so this is an indication that in order to understand shear localization, you not only diffusion, dislocation, create competition, but also you need to include the influence of grain growth, to which OPX makes huge contribution. Okay, to summarize, based on laboratory experiment, we showed that substantial weakening occurs in the lithosphere if orthopyroxene is present. In contrast, if the lithosphere were made of pure olivine, then no substantial weakening occurs, and then you cannot explain plate tectonics. Another also important from our laboratory experiment is weakening by this mechanism occurs in a temperature window. Okay? If temperature is too high, weakening doesn't occur. Too high, then the dislocation creep dominates over diffusion creep, and therefore weakening doesn't occur. And we haven't done much about it, but I expect that a small amount of water might modify weakening conditions, because we expect that water effects on rheology on OPX are likely much larger than water effects on rheology of olivine. Because general trend is if you have a more silica, degree of water weakening is larger. So this has to be addressed in order to go beyond that to discuss why Venus and if you like to explain Venus as contrast, you have two choices perhaps, like a temperature, maybe surface temperature is so different, or maybe water. So I guess I should stop here. Thank you very much.
Hi. Very interesting talk, as usual. Very simple question. Can you estimate, I don't know, for 100 million years old plate, which is the depth range over which you get this weakening with the orthopyroxene?
this is all we can do now. Okay, so we have this diagram. This is temperature and stress. I haven't done this yet, but given that, well, quick answer is no, I can't do precisely. Okay? I can give you this half conceptual model. And if you go to different temperature regime, like 100 million years, you may have a different temperature profile. And given that, and if you have a model of deformation, like a bending or something, then you can calculate the stress profile, and then you can, right, yeah, yeah. So that's the answer.
Do we have maybe one more question? Well,
So even though at a higher temperature there was no weakening, the stress was still lower than the cases that had weakening. So.
Oh yeah, well of course that's a delegate. If you go very high temperatures, it's already so weak, so you don't have to worry about it. But the main point is conceptually speaking, there's a temperature window, and I haven't done any serious work. But if, for instance, given like a surface temperature of 450 degrees C, you may ask if those temperature conditions are enough for weakening at all. So when I say high temperature, no, I'm not saying 1200 degrees or something. Laboratory conditions, this happens 1270. But if you go extrapolate to geological conditions, this critical temperature is going to be reduced.
okay. Well, in order to try and save our lunchtime, we'll